So a person stands on the surface of the Earth. The weight is given as W. And the same person stood on the surface of a planet that had twice as much mass as Earth and twice as much radius as Earth. What would the person's weight on that planet be? Well, if you remember weight, is this equal to the force of gravity? Which the force of gravity is given by G M M over R squared. Now, a couple of these things don't really matter because G is just a constant, so that doesn't really matter if we're just changing things. M is just the mass of the person, that's not changing. So really the person's weight's going to depend on the mass of the object they're standing on and the radius of the object that they're standing on. So what we could do is we could just say that the mass of this object is 1. And the radius of this object is 1. So what's 1 over 1 squared? It's just 1. So W equals 1. That's the initial condition. Now we're changing the conditions up. We're making this planet twice as massive as Earth. So what we would do is we would plug in 2 in for M. Okay. And we're making it twice the radius. So we're going to plug in 2 for R. So remember, the initial condition is just W. 1 equals W, so W is 1. But the ending condition, when we move to a different planet, it's going to be 2 over 2 squared, which is 2 over 4, which is 1/2. So that's going to give us a value of 1/2 of W, or W over 2. A particle is placed in a position where the electric field strength is 5 newtons per coulomb. If the particle will move twice as far away from the position, what will be the electric field strength? So remember, electric field strength, we'll abbreviate it as E, is equal to force over charge. Now force was K Q over R squared. Now if we divide by Q, one of those Q's goes away. So there'd be not a Q here for force, but we're getting rid of it because it's electric field strength. So a particle is placed at the position where it's 5. So basically we have 5 equals K, which is a constant, times Q over R squared. All right, so what we can do is say, all right, well, that's the value. What we could do is we could just put 1 in for R. So that means that Q would equal 5. Then what we're doing is we're going to double that distance. We're going to double it to 2. So then Q still equals 5, so we have 5 divided by 2 squared. Well, 5 divided by 2 squared is just, it's not 5 anymore. 5 divided by 2 squared is 1.25. It's 5 over 4. A satellite orbits a planet with a velocity v. What will be the velocity of a satellite that has twice as much mass and is orbiting 4 times the radius? So remember, orbital velocity comes from setting centripetal force equal to some other force. In this case, that force would be gravity. So gravity is gmm over r squared, and centripetal force is mv squared over r. Now some of this stuff cancels out. So you can rearrange this to solve for v, where v equals the square root of gm over r, where g is a constant, m is the mass of the planet, and r is the radius of the planet. So what we can do is with this equation here, we can put in values. Let's just put in a value of 1 for r. G is a constant, so it doesn't matter. So we could just put 1 in for g and 1 in for m. So you get 1 times 1 over 1. Square root of that is 1. So we just get v. That's the initial condition. Now, the satellite has twice as much mass, but that mass canceled out. That's the lowercase m here. That mass is not relevant. And it's orbiting at 4 times the radius. So only thing that changes in this equation is r is 4. So now we're going to put in 1 times 1 over 4, and the square root of 1/4 is 1/2. So the velocity would be half the velocity. So a remote-controlled toy car uses batteries that have a voltage of 8 volts, and battery storage hold charge of 1 coulomb. And the mass of the car is 1 kilogram. What's the maximum speed that the car can travel? Well, this is a conservation of energy question. Basically, the car starts with electrical energy. Electrical energy is equal to voltage times charge. That's the starting energy. And assuming that no energy is dissipated, it's going to equal the final energy, which is kinetic energy, 1/2 mv squared. Now, we have to figure out, what do we know? Well, the voltage is 8, so we have 8. That's an 8, all right? The charge is 1. 8 times 1 equals, well, 1 is the mass times 1/2, which is 0.5, times v squared. All right, so 8 times 1 is 8, divided by 0.5 is 16. 16 equals v squared. So v would equal 4 meters per second, because we just square rooted it. An electron has a mass of this, 9.11 times 10 to the minus 31st, charge of 1.6 times 10 to the minus 19 coulombs. It orbits a proton with also that same charge. An electron is traveling at 3 times 10 to the 8th meters per second. Calculate the distance between the two. Well, this one is an orbital force, centripetal force, which is mv squared over r. And that force has to come from something. It's going to come from the electrostatic attraction between the two particles, which is equal to k times q times q over r squared. Now, we're trying to solve for r. Now, that's the distance between the two. Now, this r can cancel out with one of these r's. So we have mv squared equals kqq over r. We're rearranging the solve for r. So r is going to equal, multiply it over here, divide by mv squared. It's going to equal k times q over mv squared for this particular situation. Now k is a constant. It's 9 times 10 to the 9 times 10 to the 9th. Q is 1.6 times 10 to the minus 19th. Other q is 1.6 times 10 to the minus 19th. M is 9.11 times 10 to the minus 31st. V is 3 times 10 to the 8th, but it's squared. Make sure you put parentheses around this and parentheses around this. And when you put those numbers in, you will indeed get this number right here. Now, number 6 and number 7 are about units. The equation for electrostatic force is given as F equals kqq over r squared. Which of the following would be appropriate units for k? Now, the way you solve this is to actually algebraically solve for k. If I solve for k in that equation, then I would get that k is equal to F. Then I have to multiply the r squared over, and then I would divide by q and q. So that'd be the algebraic way to solve for k. Now f, then what we do to figure out the units for k is that we would just plug in the units for everything else. So force is measured in newtons, r is measured in meters, so, and then this is squared, and then coulombs is a measure of charge, but there's two of them, not two of them, but multiplied together, so it's coulombs squared, and indeed that matches up with C. Now the units for capacitance are farads. Units for charge are coulombs, so the one that matches up with this is B. Voltage measures volts, amps measures. What's electric field strength 1 meter away from a proton? Well, if you remember, electric field strength is given by force per charge. So we can simplify that as K times Q times Q over R squared, but then divided by Q, because we're dividing the force by charge. So there's electric field strength because one of the Q's went away. Now we just plug in the numbers. K is 9 times 10 to the 9th, Q is 1.6 times 10 to the minus 19th, and R is 1. We know that K is 9 times 10 to the 9th because it's always that. It's a constant, and the charge of a proton is 1.6 times 10 to the minus 19th. It's that much charge. So when you plug those numbers in, you will indeed get A. Just make sure you put parentheses around stuff. That might help. Maybe parentheses around that, and you should get A. 9. Two charged objects are placed a distance r away from each other and experience a force of F. Two objects are then moved distance 2r, and one of the charges is tripled. What will be the force at that distance? Well, here's the equation for force. It's K times Q over R squared. And basically, what we could do is we can set an initial condition and say that R is equal to 1, and each of these Q's are equal to 1, and we get a force of F because we don't care about K because it's a constant, so it doesn't change. So if we have 1 times 1 divided by 1 squared, we just get a force of 1 Newton. F is 1 Newton. Now let's calculate the force if those values change. The K doesn't matter because it's a constant, because we're looking at how it changes, not just the value of it is. So one of the charges is tripled. So that means that the R charge doesn't really do anything either. So one of the charges is tripled, so it's 3. And the distance is 2r. So we're going to have 2 for r. So we're going to have 2 squared. So it's 3 over 2 squared, which is 3 over 4, which is 3f over 4, or 3/4 the strength. Princess Azula is a firebender that can actually produce lightning. She shoots Aang with a lightning bolt, discharges 15 coulombs of charge in 0.001 seconds. Aang's body has a resistance of 10,000 ohms. How much electrical power enters Aang's body? Now for this, if you remember, power is equal to current times voltage, IV. And voltage is equal to current times resistance, IR, V equals IR. Probably the two most important equations in circuits, or electricity equations. But understanding the idea that I, current, is also this amount of charge flowing per second. So that is the amount of charge, Q, flowing per second. Well, now we just fill in the numbers. We know that Q is 15, T is 0.001, so we have 15 over 0.001 is 15,000 amps. Now that we know that's 15,000, we know R is 10,000, so 15,000 times 10,000 is our voltage. And then we have I, we have V, we can multiply those together, and we get a huge amount of power. We get D. A circuit consists of 3 light bulbs connected in a series. They each have a resistance of 100 ohms. The 3 light bulbs are connected to a voltage of 100 volts. What's the power of the circuit? So let's draw this circuit. Here's the battery. Here's resistor 1, resistor 2, and resistor 3. That's one possible way to draw this circuit. This is 100, and each of those is 100. So if each of these is 100, remember in series, the resistance we can add up to just equal 300. You can do that in series, you cannot do that in parallel. Next question will answer about parallel circuits. So we know that the voltage is 100, and we know the resistance is 300, and we want to know the power. So if you remember, power is equal to current times voltage, which is IV, and voltage is equal to I times R. So if we combine these two equations, we could figure out that power would just equal, because we don't know I, we know it's going to equal V times I, and we don't know what I is, but we know that it's V over R, so we have V over R times V, which is V squared over R. So V squared is 100 squared over R, which is 300. Well, 100 squared is 10,000 divided by 300 is 33.3. So basically just using this equation, in this equation to solve for power. You can combine the equations if you want, or you can use 300 times, solve for I first and then plug it into here to solve for power. Whatever it is, either way you look at it, you get 33.3. So two resistors are connected in parallel. The first one has a resistance of 10 ohms. Second one is a resistance of 20 ohms. What's the total resistance or equivalent resistance? Now, since they are in parallel, you cannot add up the resistances. What you have to do is you have to use 1 over R total is equal to 1 over R1 plus 1 over R2. So 1 over R1, so 1 over R1 is 10, and R2 is 20. So when you add 1/10 to 1/20, you get 3/20. So this whole mess right here becomes 3 over 20. That's what happens when you add them together. You get 3/20. So you get 3 over 20 is equal to 1 over R. Well, we have to solve for R, so we have to take the inverse of this because 1 over R is equal to 3 over 20. So R is going to equal 20 over 3, which is 6.7. What type of circuit is shown here? Well, this is a parallel circuit. Now, a series circuit is where everything is connected one after another, where you'd have like one resistor connected to another resistor, and it's all right in a line. Parallel circuit was where there's multiple paths, like this path right here, and this path right here. There's multiple loops. So parallel circuit is a parallel circuit. Which of the following equations can we use to determine internal resistance of the battery? Well, internal resistance is little r. So basically, we need to look for an equation with little r in it. It's going to equal this one, where the EMF of the battery is equal to the current times resistance, which is just basically Ohm's law, but just more detailed because this little r is internal resistance. Since this is the only one that has little r in it, we're going to use equation A. If two resistors are connected in parallel, they have the same voltage. This is Kirchoff's rule. It says that the voltage in a loop gets used up. Going back to this circuit right here, this voltage right here, let's say this is a 10-volt battery. This voltage would be 10 volts, and then this bigger loop would also equal 10 volts. Each loop would equal 10 volts. So the voltage in each parallel circuit is the same. Contrary to that, series, if they're connected together, they're all going to have the same current because there's only one path. Imagine this was my circuit right here, but there's no path over here. It's just a single loop. Well, in this one loop, every single thing in that one loop is going to have the same current because there's only one path for the current to take. 17, which one's not equivalent to voltage? Well, let's look at it one by one. Voltage is equal to V equals IR, so that's definitely true. Voltage is also equal to energy over charge. That's the definition of voltage. It's electrical energy over charge. Since electrical energy is equal to KQQ over R, and we're dividing electrical energy is this, KQ over R, and we're dividing by charge to get voltage, well then obviously KQ over R is equal to voltage as well, where likewise Q over T is equal to current, not voltage. That's I. That's the flow of electricity. The charge on a 10 centimeter radius metal sphere is 2 millicoulombs. Which electric field strength is 10 centimeters above the sphere? Well, if you remember, electric field strength is force per charge. So electric field strength is going to equal K times Q over R squared, but we're going to divide one of those Q's out. So we only need one of the Q's here. And there's an equation for electric field strength. Now, K is 9 billion. It's 9 times 10 to the ninth. So we're taking 9 times 10 to the ninth. And then multiplying by Q, which is 2 times 10 to the minus 3. Because that's what milli means. 2 times 10 to the minus 3. Or 0.002, if you like that better. 10 to the minus 3. And we're dividing that by R, which is, we have to add these two distances together, which would be 0.2 if we convert to meters. But that R is squared. So it's a good thing to make sure you have parentheses around each of these things. You can put parentheses around that, the top and the bottom, and you will get a number of 453 million newtons per coulomb. Number 19. A 9-volt potential difference, such as 9-volt battery or something, causes a current of 3 milliamps. Now this means that we're going to use good old V equals IR to calculate resistance. Let's rearrange this out for R. R would equal V over I. And then plug in the numbers here. V is 9, and I is going to equal 0.003 because that is converted to amps, because 3 milliamps is 0.003 amps. 9 divided by 0.003 is indeed 3,000. And finally, a 1 kilowatt heater. So let's write down what we know. Power is 1,000. That's what 1 kilowatt means. So it's 1,000 watts. It's connected to a voltage of 220. So 220 is our V. And runs for 5 hours. So T is, well, it's going to be 5 times 3,600, whatever that is, because we want that in seconds. So we're going to use our equations for current. Current is equal to power divided by voltage, which is the rearrangement of P equals IV. If we do that, we get 1,000 over 220, which is 4.5 amps. So right there, that tells us that B is the right answer. Let's just double check, because energy is equal to power times time. So energy is power times time. Just rearranging that equation as well. And power is 1,000. Time is going to be 5 times 3,600. So 5 times 3,600 times 1,000 is indeed 18 million. So B is the correct answer for that one.